data sets from the last two periods. All right, yours over here, this was actually your data that you just calculated the standard deviation for. And here's period 1 this morning. That's actually probably not the exact ones, but it's very close to it. They had a real spread, 8, 10, 12, 16, 8. I mean, even though the mean came out to be very close to what your mean was, all right, they weren't very far off, all right, the spread was terrible. Their average their standard deviation was something like, I forget, but it was something like 2.47, something like that. I'm just making this up. Your standard deviation was only 0.51. Now, here's the thing. What does this tell you? Emily asked, while you're working on these, why are we learning stats? What's the point of learning stats? All right, well, I told you there's two reasons. One, I have to do it for STEM. People who are doing STEM are going to have to do research projects. They're going to need to do these kind of analyses. But there's another reason. Actually, it concerns you guys. Yes, in every lab we do, you can calculate the standard deviation and you can figure some stuff out about it. But we're about to start that section after the AP exam. I told you we're going to talk about a lot of different topics in science and society and stuff. And you ever wonder where all these bad studies come from? Okay, like you've been told 100 times. Besides on global warming, you've been told 100.
That's where they come from.
What?
Channel 1.
From Channel 1, right? Well, these stories, there are bad studies. I mean, sometimes, despite your best efforts, there's some stuff that goes on. You guys do what's called lay science. I live next to these. This is one of the stories we'll see about power lines. Well, we live next to the power lines, and you have cancer. And you live next to a power line, and you have cancer. Oh, wow, and I know somebody else that did that too. And all of a sudden, living next to power lines gives you cancer. And that was like a big scare back about 20 years ago. Cell phones causing brain tumors. Big scare. Very, very similar reason. EM radiation, all this stuff. But these aren't studies. Because it may look very impressive when you look at the data. But I got to tell you, this guy right here, it looks like, wow, here's an 8.41. And the mean is 11, so it's off by that much. That's got to be like a data point. That's got to be significant. There's something crazy about that point. Not really, because their standard deviation was so large. It's not that far off the standard deviation. Whereas if you had if your other value, if the fourth value up here was off by 3, like say it was 13.75, with a standard deviation of only 0.51, do you think that value fits with the rest of these? No. Because the standard deviation is so small, all your other stuff was pretty good. If one of those values was way off, if we had 50 values, and they were all real tight like those, but then you got one crazy one like that, you're going to have a real small standard deviation, and so you have to be able to determine how far is too far. How far outside the mean is so far that it is significant. All right. What I mean by significant is sometimes you're doing a study specifically to see if there's significance. We're going to do a t-test. Is there a difference between juice 1 and juice 2? I'll show you how we do that for a t-test tomorrow. But you also sometimes within your data want to see if there's an outlier. And that's what I want to show you how to do today with what's called a z-test. If I've got a set of data like this and I get one crazy answer but everything else is tight, probably that guy is an outlier. And I knew 40 was an outlier out of these other guys. It was obvious. Sometimes it's not so obvious. You have to have a statistical test to show if it falls outside of 2.5 standard deviations. If something falls 2.5 standard deviations outside, that's just a general rule of thumb. You can pretty much know that's significant. Like there's something that happened there, something wrong. And by the way, there are two things you can do with that. A lot of times in experiments, you do have an outlier. So what you do is you go back and you look at that. And that outlier, you might want to look at that data point, how it was gathered, and was there a calculation error? Was there an instrument error? Or was there something going on with that particular data point? Maybe there's something we didn't think about in our study. So we do another study to eliminate that as an outlier. All right, that's what you often have to do. All right, so I want you to identify, using the z-test, what kind of stuff what kind of data points would be outliers. And I can usually see them, and I can tell. When I saw this data, people thought like, oh, well, this is clearly, it's twice as big as that guy. These both can't be right. Actually, because your data has such a spread, and the standard deviation was so high, it turns out you can't throw any of these data points out. None of them are outside that 2.5 standard deviations. Whereas if you had a number that much of a difference, it absolutely would. So we're going to talk about that today. Within a data set, what numbers wouldn't fit. By the way, there's other things you can use a z-test for, too. You'll see one of the ones I'm going to use it for is the first example on there about SAT scores. If you ever want to know how well you did compared to everybody else on an SAT score, I can show you how to do that, too. All right? So let's show you how to do z-tests here. That's probably right about here. Yeah. All right. A z-score. All right. How do you do this? What does it mean? Well, the z-score basically is a measure of how many standard deviations above or below the mean is. Okay? That's kind of important. If I got a guy, sometimes remember, I'm trying to use a z-score to prove that, for example, I'm trying to do a test on something to see if it increases the growth of a plant. So if I have two results, one that grew this much and the other one that grew that much, this a chemical help it grow more, right? Well, I can see if it's statistically significant, what the chances are of it just being random. And I can do a z-score like that, or a t-test. Actually, if there's a bunch of data, you can do a t-test. So it could do how many standard deviations outside of the mean I was predicting. All right, and we can use, and what I'm going to use it for most of the time in my classes is when you get that crazy data point. I want you to see if it's an outlier or not. All right, and see if you can actually, if it's something we need to investigate or even eliminate from our experiment. And generally, a rule of thumb, although different people have different rules of thumb, a rule of thumb would be 2.5 for a z-score or greater. Now, look at how easy this formula is. Much easier than the standard deviation formula. It's just basically your data point that you're interested in minus the mean. Mu is another name for mean. I didn't say that. I mean, I did in the other class. I forgot to here. In the previous formula, we used. Previous formula we used. I finally did it. I hit the button 4 times. That's okay. We used that for the mean, right? And x was just a regular value, whatever the data point was. Mu is also a value for, and sigma, what did I say sigma represents? The standard deviation. Now the good news on these guys, listen up. You will not need to do, on these problems I'm going to give you, I'll tell you what the standard deviation is, right? Probably even tell you the mean in some cases, so you don't have all that work calculating the variance and all that stuff. But look what you do here. Just take the difference between your point and the mean and divide it by the standard deviation, so you can see how many standard deviations outside the mean you are. Okay? All right. And let me show you the example we use. There's your sample. It's right there on your paper. And I'll show you how to use the z-score chart. You take the SATs. You got 1,100 on the SATs, and the mean score for that year was 1026. Okay? You want to know what your percentage, how well did you do compared to everybody else? Well, you can figure that out if you know the standard deviation and you know the mean. You can figure out how well you did. Let me show you how. First, we'll plug it into this formula. There's the formula, and I did this right on your paper. There's your numbers plugged in, your value minus mu. And by the way, notice this will give us a positive value. What if your value was below the mean? Well, that's going to be a little bit different chart you have to use. All right? Even though the absolute amount up here will be the same, it's slightly different. You'll see why. Divided by the standard deviation, 209. Okay? You get 0.354. This tells you this. This tells me that you are 0.35 standard deviations away from the mean. And in which direction? Higher than the mean, right? So you did better than that. But that's not a very useful number. So what does that mean? Here's what you do with that number. See the chart there below? You take this first digit, right? That first digit, and you look on this column. That first digit is a 0.3. See it? Right here? So it's one of these numbers here, and then you can refine that by looking at the second digit. This 5, 0.05, see it's in the hundredths place, go to the 0.05, and it's got to be that right here. So that tells you that you did better than 63.68% of the people who took the test. Okay? All right, that's what that tells you. Okay? It's kind of cool. So you could use it for doing something like that, but you could also use it, as I said, to determine if you have an outlier, a data point amongst other data points that doesn't seem to fit. And again, what we do with those things is sometimes you could just eliminate it if you could find the reason for it, you could just eliminate it, figured it was a faulty instrument reading. That could happen. But other times, it actually generates a whole question about your experiment, and maybe you need to look into that. All right? Okay. By the way, all of this is really important, and one of the things we're going to do is going to be on that electromagnetic fields is probably the first one I'm going to show you. They talk about statistics a lot in that one, and it's an old frontline video I want to show you on that. It's really very good. All right, here's the thing. What if, I think of my second example, turn it over in a second example. I'm asking you to determine if a number is an outlier, I believe, right? Is that right? All right, and this time you actually get a negative answer, because when you subtract them, your numerator is negative. Well, this is a separate chart. You use a different chart for this. And I want to kind of explain to you why you need to use a different chart. So why couldn't I just use that other chart? Let me show you. Here's the mean. Everybody agree that this is the mean. Right down the center. Right? With the previous one we just did, you found the difference, 68.68, whatever. Okay? And it was actually the number was 0.35 higher. Right? It was 0.35 higher. Well, if it had been 0.35 lower, and you looked up 0.35, you would have gotten 68%. You would have gotten 68.68%, right? But really, the 68.38% is that side of the thing. You see what I'm saying?
Or you would need to like subtract.
Exactly. You would have to actually. There's two ways. You could use. There is a way to do this with one chart, where it only takes the percentage from the mean, and then you have to add 0.5 onto it if it's out above it, or subtract 0.5 if it's below it. I know that sounds crazy, but that's what you actually have to do. But in this case, I have a separate chart. So what I'm saying is, if I were to shade in the normal curve on the previous example, here's what I'm saying. Your test-taking skills of your 1100 meant you were better than all of this red, right? Okay? That's where you fell. You were better than all that many people. Got it? Now, if you did the exact same thing, but you were that many points below the mean, you see what I'm saying? You would look like this. You see? Yeah, but that you couldn't look up the same value on that chart. So that's why there's this chart. Now, when you use this chart, I'm not asking to actually do the percentage. I'm only asking if it's an outlier. What does that answer come out to be for your z value on that problem? Negative 2.9. So in that case, you don't even have to use a chart. All right. Is it greater than 2.5? Yes. By the way, it's positive or negative. Doesn't really matter. So that means that's a number that you should definitely be looking at. If it's in your data set, it was supposed to be the same as all those other ones, something went wrong there. Okay? And it may not be wrong, but something clearly is not consistent with that data point. All right? You have to look at that again. All right, so now you can do, on that your worksheet, you can now do numbers, where's my worksheet? Here it is. Number 8, I believe. Yes, number 8. Start with that one. And number 4. 8 and 4 you can do.